Hi, this is Leslie, and me, Sadie, and Joyce are going to talk about quantum dots and their applications. So we start off with a little bit of background. We've seen this before. This is a particle in a box model. Before we talk about quantum dots, we need to start with this model. So with this model, we start by imagining an electron that is trapped in this tiny box that it can't escape from. In physics, the electron could have energy, but in quantum mechanics, only specific energies are allowed. Each of these energies correspond to a standing wave inside of this box, and this box right here. And the electron's wave function only fits certain patterns inside of between these walls, inside these walls. This leads to the idea that energy is quantized, and an electron can only exist at certain energy levels and nothing in between. So the key idea from this model matters for quantum dots because in this model, the size of the box controls the energy, where you see if the box gets smaller, the energy levels get farther apart, but if the box gets bigger, the energy levels move closer together. This idea that confinement controls energy is sort of the foundation behind quantum dots, because a quantum dot is essentially like the physical version of this particle in the box that we've learned about. So it's one of the physical examples that we see, except the box is only a few nanometers wide, and the energy levels, they show up as light in different colors. So when we talk about this, remember, we're comparing and seeing quantum dots come to life in a particle in a box. So now that we understand more about the particle in a box, we can talk more about quantum dots. So a quantum dot is a tiny particle made from a semiconductor material that's only a few nanometers across, so very, very small. And at this size, the materials stop behaving like solids and they behave more according to quantum mechanics, where instead of having a continuous range of energy, the electrons inside the quantum dots only exist at a specific energy level, just like how it does in particle in the box. So one of the main ways quantum dots are studied is through how they interact with light. So when light shines on a quantum dot, it absorbs the energy and it excites an electron to higher energy. So when the electron relaxes, it releases photons, which is, light, and basically smaller quantum dots, as you can see here, they release higher energy, making it look blue over here, higher energy, and larger quantum dots release lower energy, which looks more red. This happens because the energy gap between levels changes with size. So, smaller dot means larger energy gap, larger dot means smaller energy gap. This is kind of similar to the particle in a box model and the energies as we've learned from it. I guess another way to think about it is also like they act like artificial atoms, where instead of having continuous energy bands, they have discrete energy levels like individual atoms do. So quantum dots does include band gap, where the band gap determines how much energy is needed for an electron to get excited. So, when the dot changes, the energy gap also changes, which directly changes the colors of the color of light that it emits. So this isn't really like a chemical change, because nothing about the material changed at all, only the size changed, but it's enough that the color changes completely.
Quantum dots are often semiconductor nanocrystals that are roughly 2 to 10 nanometers big and affect all three spatial dimensions. As a result, the size of the particle affects the band gaps and energy levels present, along with the wavelength and colors of the particle emits. Smaller dots tend to lead to larger band gaps, shorter wavelength, and higher energy, while the opposite can be said for larger particles. Some advantages of this is being able to modify the particle size to absorb more or less of the light spectrum for light trapping in solar cells to increase a device's energy creation and overall performance. This is often done by the amplification and modification of optimal characteristics that particles have. The disadvantage of this, however, is the restrictions on the transportation of charge carriers in the device's system due to this high surface-to-volume ratio and poor coupling of the quantum dot and energy levels when not properly aligned. This results in a low open circuit voltage for the system and energy loss. In order to counter these disadvantages, researchers have found that the neutralization of these effects on the shells of quantum dots and by adjusting the structural and interfacial engineering of the system have helped to balance out these issues. For an example, adjusting the interference between the quantum dots layer and the charge transport layers by stacking them allows for further advancement of the solar cell's performance in the system and the minimization of energy loss during a charge transfer. Overall, quantum dots are a prime example of how quantum mechanics is applied to solar technology and solar cells to further the understanding and development of photovoltaics on the nanoscale.
These are our citations. Thank you for watching.